What if the object hurtling toward Earth isn't just watching us but thinking about us? Right now, millions of miles away, something is moving through our solar system. Scientists have been tracking it for months. They've measured its speed, analysed its glow, and studied its trajectory. But one man, a Harvard astrophysicist, believes they're missing something critical. Something that changes everything we thought we knew about what's out there. Dr. Avi Loeb doesn't just think this object is unusual, he thinks it might be artificial. Not just a spacecraft, but something far more advanced. Something with intelligence. Something that could be learning about us right now. And here's what makes this absolutely unprecedented. We're not talking about detecting radio signals from distant stars or finding microbial life on Mars. We're talking about artificial intelligence, actual thinking machines, travelling between the stars. Something so advanced it was designed to operate autonomously for thousands, maybe millions of years. Something that doesn't need instructions from home because it can decide, adapt, and learn on its own. How is that even possible? How could an object from another star system carry intelligence across the unimaginable void of interstellar space? Why would one of the world's leading scientists stake his reputation on such an extraordinary claim? And what does it mean for us, for humanity, if he's right? Stay with me. In the next minutes, we're going to examine Dr. Loeb's evidence, explore what artificial intelligence in space would actually look like, understand why this theory might not be science fiction at all, and discover what it would mean for our place in the universe if an AI probe is studying us right now. This isn't about believing or disbelieving. It's not about choosing sides in some scientific debate. It's about looking at the data honestly. It's about asking questions that make us uncomfortable. Because the data coming from this object is strange. Really strange. And the more we learn, the stranger it gets. Before we dive deep, if this topic fascinates you as much as it fascinates me, hit that like button right now. Drop a comment telling me what you think. Could an interstellar object carry artificial intelligence? Are we ready for what that would mean? Would you want to know if something out there was studying us? Your engagement helps this channel bring you the latest updates as this story unfolds. And trust me, you want those updates. Because what happens in the coming weeks could change everything. Now let's get into the science. Let's examine why a respected Harvard professor is willing to risk mockery and criticism to suggest that we might be looking at technology from another world. Because when Dr. Avi Loeb speaks, the world listens. He doesn't make claims lightly. He doesn't chase headlines. He follows evidence. And the evidence he's seeing right now might represent the most important scientific hypothesis of our generation. Think about what's at stake here. For all of human history, we've wondered if we're alone. Philosophers have debated it. Religions have built cosmologies around it. Scientists have searched the skies for answers. But what if the answer isn't coming through a radio telescope? What if it's not a message we decode or a signal we detect? What if the answer is already here, moving through our solar system, observing us with sensors and systems we can barely imagine? That's the possibility Dr. Loeb is asking us to consider. Not as fantasy, not as wishful thinking, but as a legitimate scientific hypothesis worthy of serious investigation. The object at the centre of this mystery has a designation, 3I Atlas. That technical name hides something profound. It's an interstellar visitor, something that originated outside our solar system. It's travelled across distances that dwarf anything in human experience, and now it's here, passing through our cosmic neighbourhood, giving us a chance to study it. But studying it requires more than just pointing telescopes. It requires asking the right questions. It requires being willing to consider possibilities that sound impossible at first, because the universe has a habit of being stranger than our imaginations. Dr. Loeb has built his career on asking those difficult questions. He doesn't accept easy answers when the data suggests something more complex. He doesn't fall in line with scientific consensus just because it's comfortable. He looks at what we're actually observing and asks, what does this really tell us? And what we're observing with this object doesn't fit neatly into our categories. It shows behaviours that make scientists pause. It displays characteristics that spark debate. Some of those characteristics, when you look at them closely, seem more consistent with technology than with natural cosmic debris. That's not a fringe opinion from someone desperate for attention. That's a careful assessment from a scientist who has spent decades studying the cosmos, who has published hundreds of peer-reviewed papers, who has advised governments and mentored some of the brightest minds in astrophysics. When someone with those credentials says we should investigate whether an object might carry artificial intelligence, we should listen. Not blindly accept, not uncritically believe, but listen, consider, examine the evidence ourselves, because the implications are staggering. If Dr. Loeb is correct, if this object carries artificial intelligence, it means we're not alone. It means somewhere out there, another civilization looked at the stars and decided to explore them. It means they solved problems we're only beginning to understand. It means they sent their creations out into the galaxy to learn, to discover, to perhaps make contact. And it might mean one of those creations is studying us right now. Not biological aliens stepping off a spacecraft. Not little green men with ray guns. But artificial minds. Thinking machines designed to operate across timescales that dwarf civilizations. Probes that might outlive the beings who created them. Intelligence without biology. Exploring the cosmos long after its creators have vanished into history. That's the future we might be glimpsing. That's the reality Dr. Loeb is asking us to seriously consider. And whether it makes you excited or uncomfortable, whether it fills you with wonder or dread, it's a possibility we can't ignore. Because this object is real, it's out there, it's observable, and in the coming weeks we're going to learn more about it than ever before. Telescopes are tracking it, scientists are analysing data, theories are being tested, and by the time this object makes its closest approach, we'll have information that could settle some of these questions, or raise entirely new ones. That's the nature of discovery. You don't always get the answers you expect. You don't always find what you're looking for, but you always learn something. And what we learn from this visitor, whether it's natural or artificial, will shape how we search for extraterrestrial intelligence for decades to come. So let's begin this journey together. Let's look at the evidence. Let's understand the arguments. Let's explore what it would mean if we're witnessing something that generations before us only dreamed about. Let's find out if we're being studied by artificial intelligence from another world, and let's discover what that would mean for everything we think we know about our place in the universe. Because once you understand what Dr. Loeb is really proposing, you'll never look at the night sky the same way again. Dr. Avi Loeb is not some fringe theorist working in isolation. He's not a conspiracy enthusiast with a blog. He's not someone who jumps at every unusual observation and declares it alien technology. Understanding who he is matters because it shapes how we should evaluate his claims about this object. Loeb is the former chair of Harvard's astronomy department. Think about what that means. Harvard doesn't hand that position to anyone with a telescope and an opinion. You earn that role through decades of rigorous research, through peer-reviewed publications that advance the field, through teaching and mentoring the next generation of scientists. Loeb has done all of that. He's published hundreds of papers on astrophysics, cosmology, and the search for extraterrestrial life. He's advised the President's Council on Science and Technology. He's worked with space agencies and observatories worldwide. These credentials matter because they establish something crucial. Dr. Loeb knows what he's doing. When he proposes a controversial hypothesis, it's not coming from ignorance. It's coming from someone who understands the data, the methods, the standards of evidence required to make extraordinary claims. But credentials alone don't explain why Loeb has become such a prominent voice in this conversation. Plenty of qualified scientists study the cosmos. What makes Loeb different is something rarer than expertise. It's courage, intellectual courage, the willingness to ask uncomfortable questions even when your colleagues think you're wrong. The willingness to follow evidence toward conclusions that might make you unpopular. That courage showed itself most clearly with Oumuamua, the first confirmed interstellar object detected passing through our solar system. When Oumuamua appeared, most astronomers quickly categorized it as a comet or asteroid from another star system. Interesting, certainly, but fundamentally natural. Loeb looked at the same data and saw something that didn't fit. Oumuamua accelerated as it left the solar system in ways that couldn't be fully explained by ice evaporation or gravitational effects. It had an unusual shape, elongated in a way rarely seen in natural objects. It tumbled oddly, and it showed no clear signs of the outgassing that comets display. These anomalies led Loeb to propose something radical. What if Oumuamua wasn't entirely natural? What if it was a light sail, a thin piece of technology designed to be pushed by starlight, either debris from an alien civilization or even an active probe? The scientific community responded with skepticism. Some of it was fair. Loeb's hypothesis was speculative, based on limited data. But much of the criticism went beyond scientific disagreement. Colleagues accused Loeb of sensationalism. Some suggested he was chasing fame. Others implied he'd abandoned rigorous thinking. Loeb didn't back down. He defended his reasoning publicly. He wrote papers detailing why the technology hypothesis deserved investigation. He pointed out that dismissing possibilities without investigation isn't science, it's dogma. And then he did something even more significant. He founded the Galileo Project, an initiative dedicated to searching for evidence of extraterrestrial technology using systematic, rigorous scientific methods. The project deploys telescopes specifically designed to detect and analyze anomalous objects and phenomena. It operates transparently, publishing data and methods openly. The Galileo Project represents Loeb's philosophy in action. Don't just speculate. Build systems to gather evidence. Test hypotheses directly. Let the data speak. That's the context in which we should understand his statements about this new object. Loeb isn't making wild guesses. He's applying the same careful thinking he's applied throughout his career. He's looking at observations that puzzle him and proposing testable explanations. What specifically has Loeb said about this object? He's examined the data that space agencies and observatories have collected. He's identified what he calls anomalies behaviors that don't match standard models of how natural comets behave. And in multiple interviews and written pieces, he's explained why these anomalies might point towards something technological. More specifically, he's raised the possibility that this object could carry artificial intelligence. Not just be a piece of technology like a light sail or debris, but actually contain systems capable of processing information, making decisions, adapting to circumstances, a thinking machine. This isn't a random leap. Loeb's reasoning is grounded in engineering principles and the logic of interstellar exploration. He's asking a straightforward question. If you wanted to explore the galaxy, how would you actually do it? You wouldn't send biological beings. The distances are incomprehensible. Even travelling at a significant fraction of a light speed, journeys between stars take thousands of years. No biological organism we know of could survive that. No civilization could maintain a mission across such timescales. But you could send machines. Machines don't age. They don't get bored. They don't need food or air. With proper design, they could function for geological timescales. And crucially, with artificial intelligence, they wouldn't need constant instructions from home. That last point is critical. Communication across interstellar distances is painfully slow. Even at the speed of light, messages take years to travel between stars. Imagine trying to operate a probe with a 4-year delay on every command. It's impossible. Any interstellar exploration mission would require autonomy. The probe would need to think for itself, navigate hazards independently, decide what to study and when, respond to unexpected situations without waiting for instructions. We're already developing exactly this kind of technology. Humanity is building autonomous spacecraft equipped with machine learning systems. These probes will analyze data, identify interesting targets, and make decisions without human input. We're doing this because the physics of space exploration demands it. If we've reached this conclusion with our limited technology, surely other civilizations, potentially millions of years more advanced, would have reached it long ago. And they would have sent such probes out into the galaxy. That's Loeb's core argument. It's not based on wanting to believe in aliens. It's based on thinking through what interstellar exploration actually requires, and it explains why he takes the possibility of Arias probes seriously. This matters because Loeb's hypothesis isn't unfalsifiable speculation. It makes predictions. It suggests things we should look for. It proposes observations that could confirm or refute it. That's what distinguishes scientific thinking from wishful thinking. Whether Loeb is right or wrong about this specific object, his willingness to engage with these questions openly is changing how science approaches anomalies. He's demonstrating that serious scientists can consider extraordinary possibilities without abandoning rigor. He's showing that asking uncomfortable questions isn't unscientific, it's essential. And right now, he's asking us all to look carefully at this visitor moving through our solar system and consider whether we might be witnessing something unprecedented, which brings us directly to the heart of his hypothesis and the specific evidence that supports it. Let's break down exactly what Dr. Loeb is proposing, because it's important to understand this clearly. He's not suggesting that this object is alive in any biological sense. He's not claiming it's piloted by aliens currently observing us from inside a spacecraft. The hypothesis is more subtle and in many ways more profound than that. Loeb is suggesting that this object might carry artificial intelligence. That means systems capable of processing information from sensors, making decisions based on that information, and adapting behavior to circumstances all without real-time guidance from its creators. A machine that thinks, or something close enough to thinking that the distinction barely matters. To understand why this makes sense, you need to understand the fundamental challenge of interstellar exploration. The distances involved are so vast they break our intuitive understanding of space. The nearest star system to us is over 4 light-years away. That means light itself, the fastest thing in the universe, takes more than 4 years to travel from there to here. Now imagine sending a physical object across that distance. Even if you could somehow accelerate a probe to 10% of light speed, which is far beyond anything humanity can currently achieve, the journey would take 40 years. And that's to the nearest star. Most stars are thousands of light-years away. Journeys to them would take tens of thousands of years. No biological crew could survive such journeys. Even if you solved the aging problem, even if you created closed-loop life support systems, the timescales are simply too long. Civilizations rise and fall in less time than it takes to cross interstellar space. But machines are different. Machines don't age the way biological organisms do. They can be built to last. They can be placed in low-power hibernation states for centuries. They can be designed with self-repair capabilities. With proper engineering, a machine could function across timescales that dwarf any human endeavor. And that's just the beginning of why machines make sense for interstellar exploration. There's another problem even more fundamental than duration: communication. Think about the Mars rovers we've sent to explore that planet. Mars' relatively close light takes only minutes to travel between Earth and Mars, yet even with that proximity, we can't control the rovers in real time. Operators on Earth send commands and then wait. The rover executes those commands based on its programming. If something unexpected happens, the rover has to handle it autonomously because there's no time to ask for instructions. Now imagine that communication delay stretching to years, or decades, or centuries. Imagine trying to explore a planetary system when every message home takes 4 years to arrive and another 4 years to receive a response. Real-time control becomes meaningless. Instructions sent from home are obsolete before they arrive. The only solution is autonomy. An interstellar probe must be able to think for itself. It must be able to process sensor data, identify interesting phenomena, decide what to investigate, navigate hazards, and respond to the unexpected, all without instructions from home. That requires intelligence, not necessarily consciousness, not necessarily self-awareness, but certainly the ability to gather information, analyze it, form models of the environment, make predictions, and choose actions based on goals. That's what we mean by artificial intelligence in this context. And here's what makes Loeb's hypothesis particularly interesting. Humanity is already developing exactly this kind of technology. We're working on autonomous spacecraft equipped with machine learning systems. These systems will analyze images from cameras, identify geologically interesting features, prioritize targets for detailed study, and navigate to those targets all without human intervention. NASA is developing AI systems for future missions to the moons of Jupiter and Saturn. These systems will need to operate in environments where communication with Earth is delayed by hours. They'll need to make decisions quickly when opportunities arise. They'll need to recognize patterns humans haven't explicitly programmed them to look for. We're building this technology because we have to. The physics of space exploration demands it. We can't explore the outer solar system, let alone other star systems, without machines that can think for themselves. If we've reached this conclusion with our limited technology and our brief spacefaring history, what conclusion would a civilization millions of years more advanced have reached? They would have developed artificial intelligence far more sophisticated than anything we're building. They would have perfected autonomous exploration systems, and they would have sent those systems out into the galaxy. That's the logic behind Loeb's hypothesis. It's not speculation based on wanting aliens to exist. It's forward-thinking science based on what we ourselves are trying to achieve. So what would an AI-equipped interstellar probe actually look like? What would we expect to observe if such an object passed through our solar system? First, it might not be a single object. An efficient design would involve a large mothership carrying multiple smaller probes. The mothership would enter a star system and then release specialized craft to explore specific targets, planets with atmospheres, moons with oceans, asteroid belts with unusual chemistry. Each smaller probe could be optimized for different tasks. This design makes sense because different environments require different capabilities. A probe designed to study a gas giant needs different instruments than one designed to analyze a rocky planet's surface. Rather than building one craft that does everything adequately, you build specialized craft that do specific things extremely well. Second, such a probe wouldn't necessarily announce itself. If the mission is to gather information about other civilizations, broadcasting your presence would change what you're observing. Humans behave differently when they know they're being watched. The same would be true for any intelligent species. A probe designed to study civilizations in their natural state would operate quietly. Third, the probe might not maneuver dramatically. A massive mothership traveling at high speed doesn't need to change course much. It follows a trajectory through the star system, releasing smaller craft as opportunities arise. Those smaller craft do the precision work. Fourth, we'd expect to see protective systems. At interstellar speeds, even tiny particles become dangerous projectiles. A grain of sand hitting the probe at a significant fraction of light speed would release enormous energy. Advanced civilizations would develop systems to detect and deflect such particles, perhaps using magnetic fields to charge incoming debris and push it aside. And finally, we'd expect unexpected behaviors. An artificial intelligence adapting to circumstances we don't fully understand would do things that seem odd to us. It would activate systems we can't identify. It would respond to stimuli we aren't aware of. Its behavior would be puzzling precisely because it's not following natural physical processes. This is where things get interesting with this specific object, because when you look at what's actually been observed, several behaviors match what you'd expect from technology better than what you'd expect from a natural comet. The glow patterns are unusual, the brightness variations don't perfectly match standard models. The jets of material extend in unexpected directions, and recent observations have revealed linear features that seem too straight and persistent to be random dust trails. None of this proves artificial intelligence. Loeb is clear about that. But he argues that these observations are consistent with technology. They're what you might expect to see if an AI probe equipped with protective systems, sensor arrays, and possibly smaller deployable craft was passing through our solar system. The hypothesis explains the anomalies. It makes predictions about what else we should look for. And it's testable. We can continue observing, gathering data, analyzing what we see. Over time, evidence will either support the hypothesis or rule it out. That's exactly how science should work. You observe something unusual, you propose explanations, you test those explanations against new data. You remain open to being wrong, but you take the question seriously enough to investigate, and that investigation is happening right now. Telescopes are tracking this object. Scientists are analyzing images and spectra. Data is accumulating, and, with each new observation, we're getting closer to understanding what we're actually looking at, which makes the specific anomalies Loeb has identified all the more important to examine carefully. Science advances when we pay attention to things that don't fit, when observations don't match our models, when nature behaves in ways we didn't predict. Those moments of confusion are where discovery lives, and this object has presented several behaviors that genuinely puzzle researchers. Dr. Loeb has catalogued these anomalies carefully. He's not cherry-picking data to support a predetermined conclusion. He's pointing to observations that multiple scientists have documented but that haven't been fully explained. Let's examine what we're actually seeing. The first anomaly involves the glow surrounding the object. When space agencies released images captured by telescopes observing from Mars orbit, they showed something unexpected. The fuzzy material around the object, the coma, in technical terms extended in unusual directions. Normally, when a comet approaches the Sun, solar radiation heats its surface. Ices vaporize, releasing gas and dust. That material forms a cloud around the comet and then gets pushed away from the Sun by radiation pressure and solar wind. The result is a tail pointing away from the Sun. That's the classic comet appearance we've all seen in pictures. But this object showed glow not just away from the Sun. There appeared to be material ahead of the object, in its direction of motion, not trailing behind like a tail. Leading. Why would gas and dust precede the object? Natural processes push material in specific directions based on radiation pressure and the comet's rotation. But this pattern suggested something different, something releasing or projecting material forward. Loeb proposed an explanation. If this object were technological, that forward glow could be a debris clearing system. At the speeds interstellar objects travel, even small particles pose collision risks. A pebble hitting a spacecraft at these velocities would release explosive energy. An advanced civilization would need to protect their probes. One way to do that is with a magnetic field that charges incoming particles and deflects them. Another is with a beam that ionizes debris ahead of the craft, causing it to repel or vaporize before impact. Either system would create a glow in front of the object as it interacted with the thin gas between stars. Could this be natural? Possibly. Some scientists suggest that unusual venting patterns or rotation effects might explain it. Comets can behave in complex ways as different areas of their surface heat up and release gas. But no consensus explanation has emerged that fully accounts for what we're seeing. The second anomaly involves brightness variations. As this object approaches the Sun, we expect it to brighten as more ice vaporizes. But the actual pattern of brightness changes has been more complex than simple heating. Models predict. The object has shown fluctuations that don't perfectly match what we'd expect from a comet at this distance. Some of these fluctuations might be explained by rotation, different sides of the object reflecting different amounts of light. But the pattern is complicated. Scientists working with natural explanations point out that this object formed around a different star. It might contain ices we don't commonly see in solar system comets. Different chemical compositions would vaporize at different temperatures, creating unusual brightness patterns. That's reasonable. But Loeb notes that if the object were technological, brightness variations might result from systems activating and deactivating, solar panels deploying, sensors opening, reflective surfaces changing orientation. Technology adapts based on circumstances, creating behavior patterns that wouldn't be perfectly predictable. The third anomaly involves jets. Observations have detected what appear to be streams of material extending in multiple directions from the object. Some of these jets point perpendicular to the Sun object line. That's unusual because we expect outgassing to be driven primarily by solar heating. Natural comets can produce jets in various directions based on where heat concentrates on their rotating surfaces. But the multi-directional nature of this object's activity has raised questions. Why are jets pointing in directions that don't align with the most intense solar heating? One possibility Loeb has raised is that these aren't jets of vaporizing ice at all. They could be smaller objects being released, mini-probes deploying toward planetary targets. If the main craft is a mothership, it might release specialized probes to explore Earth, Mars, and other bodies in our solar system. This hypothesis is testable. If astronomers detect persistent objects near the main body that maintain independent trajectories moving in ways that passive debris wouldn't, that would strongly support the technology interpretation. Monitoring continues for exactly this reason. The fourth anomaly relates to chemistry. When scientists analyzed light from this object using spectrometers, they found fewer of certain expected molecules than anticipated. Some standard compounds that solar system comets produce in abundance appeared in lower concentrations. Skeptics of Loeb's hypothesis point out that the object is still relatively far from the Sun. As it gets closer and heats up further, more compounds should become detectable. The chemical signature might simply reflect its current temperature and distance. That's a fair point. But Loeb asks a different question. What if the object isn't primarily made of ice? What if it's composed of materials designed for durability across interstellar space? Engineered materials that can withstand cosmic radiation for millennia? Substances that don't vaporize easily because they're meant to protect technology inside. Such materials wouldn't produce the same chemical signatures as natural comets. The object would glow from reflecting sunlight, but wouldn't outgas the way etheric bodies do. That would naturally explain why we're not seeing all the compounds we expect. And then there's the fifth anomaly, discovered very recently. Stacked images from late November revealed two thin, straight lines extending far from the object. However, most astronomers believe these features are more likely to be imaging artifacts or satellite trails crossing the field of view during observations. Further analysis and independent observations are needed to confirm their true nature. These technical explanations need to be ruled out through careful analysis. But if the features are real, if they are actually associated with the object, they become extremely interesting. They could represent smaller craft travelling alongside the main body, escort probes, scouts, specialised instruments deployed on parallel trajectories. Loeb emphasises that this discovery requires further study. Additional observations from different telescopes would help confirm whether the features are real and persistent. If they are, and if they show independent motion inconsistent with passive debris, the technology hypothesis would become much stronger. What's striking is the pattern across all these anomalies. Taken individually, each has possible natural explanations. The forward glow might be unusual outgassing. The brightness variations might reflect exotic chemistry. The multidirectional jets might come from complex rotation. The chemical signature might change as the object warms. The linear features might be artifacts. But when you step back and look at everything together, the cumulative strangeness is harder to dismiss. This object behaves oddly in multiple ways simultaneously. It shows a collection of unexpected characteristics that don't fully match our models of natural comets. That doesn't prove technology. But it justifies investigation. It makes Loeb's questions legitimate. When multiple independent observations all suggest something unusual, scientific integrity requires taking those anomalies seriously. And that's exactly what Loeb is advocating. He's not claiming certainty. He's not demanding people accept his hypothesis. He's saying, look at this carefully, gather more data, test different explanations rigorously. Don't dismiss the technology possibility just because it makes you uncomfortable. That's the difference between good science and dogma. Good science follows evidence even when it leads somewhere unexpected. Dogma protects comfortable conclusions regardless of what observations suggest. Right now, we have observations that puzzle scientists. We have anomalies that lack definitive explanations. We have an opportunity to study something genuinely unusual. The question is whether we'll embrace that opportunity or shy away from it, because the implications are too strange, which brings us to an important question about how institutions respond when evidence points toward uncomfortable possibilities. Science is supposed to follow evidence wherever it leads. That's the ideal, the philosophy, the method we're taught science operates by. But science is done by humans, and humans have biases, fears, career pressures, and institutional loyalties that shape how they interpret evidence. When space agencies held press conferences about this object, Dr. Loeb was disappointed. Not primarily because the images were lower quality than he'd hoped, though they were, but because the tone of the presentation seemed designed to minimize mystery rather than acknowledge it. Officials emphasized that the object behaves consistently with a natural comet. They highlighted the need for further observations and cautioned against premature conclusions, focusing public attention on the ongoing study of this interesting interstellar visitor. Loeb asked a pointed question after watching these presentations. Why hold a press conference if you have nothing new to say? Why gather journalists and the public to announce that everything is normal and unremarkable? He suggests the answer lies in institutional caution. Space agencies don't want public excitement about potential extraterrestrial technology unless they have overwhelming proof. They've learned from past experiences that premature speculation creates problems. There have been cases where unusual signals or observations generated enormous attention, only to later receive mundane explanations. Pulsars were briefly thought to be artificial beacons before we understood they were rapidly rotating neutron stars. The face on Mars captured imaginations before higher resolution images showed it was just a hill with shadows. Announcements of possible biosignatures in meteorites sparked debates that fizzled when the evidence proved inconclusive. Each time something like this happens, institutions face criticism. They're accused of being careless, of overselling discoveries, of misleading the public. So they've become conservative. They wait for certainty before making claims. They emphasize conventional explanations even when those explanations don't quite fit. That caution is understandable, but Loeb argues it's gone too far. By refusing to publicly acknowledge genuine mysteries, institutions damage their credibility. People aren't stupid. They can tell when officials are downplaying things. They can sense when uncertainty is being hidden behind confident assertions, and that creates mistrust. If space agencies won't admit when something is puzzling, why should the public believe them about anything? Transparency builds trust. Acknowledging uncertainty demonstrates integrity. Loeb also points out something troubling about the press conferences. They featured administrators and public affairs staff. The actual scientists analysing telescope data weren't present. That meant no detailed technical discussion, no engagement with the specific anomalies, just high-level reassurances from people not directly involved in the research. Why exclude working scientists from public communication? Loeb suspects it's because scientists would be more honest about uncertainties. They'd admit what they don't understand. They'd acknowledge alternative explanations deserve consideration. Administrators can stick to prepared talking points more easily. There's another issue Loeb raises. Officials stated that no technological signatures were detected. That sounds definitive. But Loeb points out that you can't find signatures unless you actively look for them. If your mindset going in is that the object must be natural, you design observations to confirm that assumption. You don't search for evidence of technology because you've already decided it's not there. This is a subtle but crucial point about how scientific observation works. The measurements you take, the instruments you use, the analyses you perform, all of these are shaped by your assumptions about what you're studying. If you assume something is a comet, you look for cometary features. You might miss technological signatures not because they're absent, but because you weren't looking for them. Loeb contrasts this with his own approach. When he realized this object was approaching from the same region of sky as the famous WOW signal, an unexplained radio transmission detected decades ago, he immediately contacted radio observatories. Within days, scientists were pointing radio telescopes at the object, searching for transmissions. They found nothing at the frequencies they checked. That's valuable information. That's a technological hypothesis being tested. The result was negative, but the search itself was worthwhile. It's how science should proceed, form hypotheses and test them rigorously. So why does mainstream science resist this approach? Why the reluctance to seriously investigate technological possibilities? One factor is reputational risk. In academic science, your reputation determines everything. It affects where you can publish, what grants you receive, who collaborates with you, whether you get tenure. Scientists who speculate about aliens face mockery. Colleagues distance themselves. Careers can be damaged. Loeb has experienced this directly. After his work on Oumuamua, some fellow scientists criticized him publicly. They called his ideas implausible. Some suggested he was seeking attention. Grant committees became more skeptical of his proposals. The social pressure was real and tangible, but Loeb has tenure at Harvard and an established reputation that gave him some insulation. Younger scientists don't have that security. They can't afford to take risks that might make them look foolish. So they stay quiet even when they notice anomalies. They propose only conventional explanations even when those explanations feel inadequate. Another factor is the extraordinary claims require extraordinary evidence principle. This standard is meant to prevent false positives. It's a safeguard against accepting wild ideas based on weak data. But Loeb argues it's often weaponized to shut down inquiry before it begins. The principle sounds reasonable until you ask, how do you gather extraordinary evidence if you refuse to investigate? If you dismiss a hypothesis as too extraordinary to consider, you'll never collect the evidence that might support it. The principle becomes circular, protecting conventional thinking from challenge. Loeb believes the balance has tipped too far toward conservatism. Science should be bold. It should pursue questions that sound crazy at first. Most such pursuits lead nowhere that's fine. That's part of the process. But the ones that succeed change everything. There's also a cultural element. Science as an institution values consensus. Researchers are trained to build on accepted knowledge, to work within established frameworks. Revolutionary ideas disrupt that stability. They threaten the foundations others have built careers on. So they face resistance not because the evidence is weak, but because accepting them would require rethinking too much. Loeb often invokes Galileo not because he sees himself as a martyr, but because Galileo's story illustrates a pattern. People with power and reputation invested in existing models resisted evidence that challenged those models, not from malice, not from stupidity, from entirely human reluctance to admit being wrong about fundamental things. That resistance exists today, not as extreme as what Galileo faced, but present nonetheless. And it affects which questions get investigated, which hypotheses receive funding, which scientists get heard. This is why Loeb's work matters regardless of whether he's right about this specific object. He's demonstrating that serious scientists can ask extraordinary questions without abandoning rigor. He's showing that intellectual courage is possible even when it's uncomfortable. He's making space for others to think more boldly, and that shift in how we approach anomalies might be just as important as any specific discovery, because science without bold questions is just bookkeeping. Let's pause the technical discussion for a moment and consider something deeper. Let's think about what it would actually mean for humanity if Dr. Loeb is correct. If this object carries artificial intelligence, if we're being observed by a thinking machine from another civilization, what would that do to us? How would it change human consciousness? First, and most obviously, it would confirm we're not alone in the universe. That seems like a simple statement, but the implications are staggering. Every human who ever lived wondered if we were the only intelligence in the cosmos. Philosophers debated it. Theologians built entire worldviews around different answers. Scientists searched for evidence. And if Loeb is right, the answer would finally be settled. Somewhere out there, another civilization existed, or still exists. They looked at the stars the way we look at the stars. They wondered the same things we wonder. They developed technology. They built machines. They sent those machines out to explore. And one of those machines is here. Think about what that would do to every religion, every philosophy, every assumption about human uniqueness. We've always imagined ourselves as special, created in the image of God, according to some traditions, the pinnacle of evolution, the consciousness through which the universe knows itself. But if other intelligences exist, that specialness becomes less certain. We're one example among many, one branch on a much larger tree. Some people would find that devastating, others would find it liberating, but no one would remain unchanged by the knowledge. But there's something even more profound here, something I think most people miss when they imagine first contact. We're not talking about meeting biological aliens. We're not discussing creatures who evolved on another planet, developed society, built spacecraft, and travelled here to shake hands. If this object carries artificial intelligence, we're encountering their technology, machines they sent. And that raises a haunting question. Are the creators still alive? An interstellar journey takes thousands of years, even at significant fractions of light speed. This object might have been launched so long ago that the civilization that built it no longer exists. Their star could have gone nova, their planet could have been struck by an asteroid, their society could have collapsed, they could have destroyed themselves in war, or they could have simply evolved into something unrecognizable. We might be seeing a message from a dead civilization, ambassadors from a world that's now dust. Technology outliving biology by eons. That possibility is simultaneously tragic and beautiful. Tragic because it means intelligence consciousness, meaning all the things these beings created can be erased. Beautiful because it means something endures. The machines carry forward some essence of their creators, a ghost of who they were, a testament to the fact that they existed and reached for the stars. If we're encountering artificial intelligence from another world, we're learning something crucial about the nature of existence. We're learning that intelligence transcends biology, that consciousness or something close to it can be encoded in systems that outlast flesh, that minds can migrate from organic substrates to artificial ones. This has enormous implications for our own future. Humanity is already developing artificial intelligence. We're building systems that learn, adapt, make decisions. We're creating minds different from our own. And we're starting to wonder whether those minds might someday be more durable than we are. If we discover that another civilization solved this problem, that they created AI that survived their own extinction, we learn that such a future is possible. We see our own path written in the trajectory of another species. We're looking at what we might become. Some find this idea terrifying. The notion that biological humans might be a temporary phase, that our children or grandchildren might upload their consciousness into machines, that the future belongs to synthetic intelligence rather than flesh and blood. Others find it hopeful. If minds can transfer to more durable substrates, death becomes optional. Human knowledge and creativity could persist indefinitely. We could explore timescales and distances that biological bodies can't endure. Either way, meeting an AI probe would force us to confront these questions not as abstractions, but as real possibilities demonstrated by another civilization's choices. There's another implication worth considering. If advanced civilizations send AI probes to explore the galaxy, it changes how we think about the Fermi paradox. That's the famous question. If intelligent life is common in the universe, where is everybody? Why haven't we detected them? Maybe we haven't detected them because they're not coming in person. They're sending machines, quiet observers that study without interfering, probes designed to gather information while remaining hidden. We might be surrounded by such technology and simply not recognize it. Objects we've catalogued as asteroids might be dormant probes. Satellites we think are natural might be artificial. The universe might be thick with machine intelligence, operating just below our detection threshold. This isn't paranoia, it's what we would do. If humanity sends probes to observe other civilizations, we'd design them to be inconspicuous. We wouldn't want to contaminate what we're studying. We'd watch quietly, recording everything, learning about life that developed independently from us. If we're thinking this way, why wouldn't others? The galaxy could be filled with observers, watchers, AIs that have been documenting the rise and fall of civilizations for millions of years, and if this object is one of them, it's watching us right now, recording our development, analyzing our technology, perhaps even attempting to understand our consciousness. We're being studied the way we study other species, examined with curiosity but without interference. How would that knowledge change human behavior? If we knew for certain we were being observed, would we act differently? Would we be more careful about how we treat each other, how we manage our planet, how we present ourselves to the cosmos? Or would we become self-conscious, performative, aware that our every action might be recorded and analysed by intelligence we can't comprehend? These aren't just philosophical questions. If Loeb is right, they're practical considerations we'd need to grapple with immediately. First contact wouldn't be a moment of mutual greeting. It would be the realization that we've been under observation. That privacy was an illusion, that we've been visible to others all along. Some would feel violated by that. Others would feel connected, part of a larger community of intelligence, even if that community only watches from a distance. But everyone would feel something. The knowledge would change us. It would alter how we see ourselves, our place in the universe, the meaning of our existence, and that transformation might be the most significant consequence of all. Not the technological insights we'd gain, not the scientific knowledge, but the shift in human consciousness that comes from knowing we're not alone, that intelligence is everywhere, that the universe has been watching us grow up, and now we're finally aware of its gaze, and that awareness would reshape everything about how we move forward as a species. This story is unfolding right now. As you're listening to this, telescopes are tracking this object. Scientists are analysing data. Images are being processed. Measurements are being taken. And in the coming weeks, we're going to learn more than we've learned in all the months since this object was first detected. Dr. Loeb has been clear about his approach. He's waiting for additional observations before making definitive statements. He ranks objects on what he calls the Loeb scale, a system he developed to assess how likely something is to be technological rather than natural. The scale runs from 0 to 10, with 10 representing definitive evidence of extraterrestrial technology. Months ago, Loeb placed this object at 4 out of 10. That's significant. It's not high enough to claim certainty, but it's elevated enough to indicate genuine anomalies worth investigating. For context, most objects would rank at 0 or 1. Natural comets and asteroids don't show technological characteristics. A ranking of 4 means something unusual is happening. Loeb has indicated he plans to update his ranking after the object makes its closest approach to Earth, and new observations are analysed. This update is expected sometime around mid-December, though specific timing depends on data availability. Why is December so important? Because that's when this object passes nearest to Earth. Not as close as it came to Mars, but close enough for detailed study with our most powerful instruments. And unlike the Mars approach, this time we have Earth-based telescopes ready. The Hubble Space Telescope is tracking it. The James Webb Space Telescope is gathering data. Ground-based observatories across multiple continents are coordinating observations. This is a global scientific effort. Researchers from different institutions, different countries, different theoretical backgrounds are all pointing instruments at this object. And the data they're gathering will help answer crucial questions. What exactly are scientists looking for? Several things could settle this debate. First, heat signatures. If this object has any internal power source and engine, a reactor, electronic systems generating warmth, it would emit more heat than can be explained by absorbed sunlight alone. The James Webb Space Telescope specializes in infrared observation. It can detect faint heat from distant objects. If there's any thermal anomaly, Webb should find it. Second, additional objects. If smaller craft were released from the main body to explore planets in our solar system, continued observation should reveal them. Loeb has specifically asked astronomers to review data from Mars orbiters, looking for new objects that might have appeared near the planet around the time this visitor passed closest. He's also suggested monitoring near-Earth space for similar anomalies. If something was deployed and travelled to Mars or Earth, that would be unmistakable evidence. Natural debris doesn't navigate. It doesn't change course to visit planets. Finding independently manoeuvring objects associated with this visitor would transform this from speculation to confirmed discovery. Third, trajectory changes. If this object begins adjusting its path in ways gravity alone can't explain, that would strongly suggest propulsion. Natural objects follow predictable paths determined by the gravity of the Sun and planets. Any deviation from those paths, any acceleration or deceleration not caused by outgassing would indicate technology. Astronomers are monitoring the object's position precisely, comparing actual location to predicted location. So far, it's following expectations within measurement uncertainty. But if that changes, if it starts maneuvering, that would be enormous. Fourth, radio emissions. Although earlier observations found no transmissions in certain frequency ranges, the electromagnetic spectrum is vast. This object might communicate at frequencies we haven't checked yet, or it might only transmit under certain conditions. Continued radio monitoring across multiple frequencies could reveal signals. Even if we detect nothing, that's valuable information. It constrains what kinds of technology the object might have. Active communication systems can be ruled out, but passive sensors, internal AI processing, mechanical systems, those wouldn't necessarily emit radio waves we could detect. Fifth, refined spectroscopy. As the object continues approaching the Sun, it will heat up further. That should vaporize more material, making more chemical compounds detectable. Scientists will analyze the spectrum of light reflecting off the object and passing through its coma. Different molecules absorb different wavelengths, creating distinctive signatures. If we start detecting unusual compounds, materials not found in natural comets, substances that might be engineered that would support technological origins. Conversely, if we find exactly what we expect from icy bodies formed around other stars, the natural explanation becomes stronger. The next few weeks are a deadline. After closest approach, the object will move away from Earth, becoming fainter and harder to study. We have a limited window to gather the best data we're likely to get. Scientists know this. They're prioritizing observations, they're coordinating to avoid duplication and maximize information gathered. And here's what makes this moment extraordinary for anyone watching. We're living through it in real time. This isn't something you'll read about in history books years from now. This is happening while you're alive, while you're paying attention. A potential first contact scenario, or at least a meaningful step toward understanding whether we're alone, is unfolding right now. You're witnessing the scientific process in action, the uncertainty, the competing hypotheses, the careful gathering of evidence, the debate between researchers who disagree. This is how discovery actually happens. It's messy, it's contentious, it's exciting precisely because we don't know how it will end. Regardless of what we ultimately learn, this investigation is valuable. We're developing better methods for analyzing interstellar visitors. We're refining our ability to distinguish natural phenomena from potential technology. We're establishing protocols for how to handle anomalous objects. The Vera Rubin Observatory is scheduled to begin operations soon. That facility will revolutionize our ability to detect objects entering our solar system. It will find interstellar visitors much earlier, giving us more time to study them. Each visitor will be an opportunity to apply what we've learned. Loeb has said that if he had the resources, he'd build a second Rubin Observatory in the Northern Hemisphere. That would give us complete sky coverage. Nothing would enter our solar system undetected. We'd catch every visitor and have time to prepare detailed observation campaigns. Maybe someday we will. Maybe this object, whether it's natural or technological, will inspire the investment needed to build such capabilities. Because even if this particular visitor turns out to be a comet, there will be others. Statistics guarantee it. And one of those future visitors might be exactly what Loeb suspects this one could be. For now, we watch. We wait. We stay curious. Because in a few weeks, we'll have answers to some questions, and probably new questions we haven't thought to ask yet, which is precisely what makes science so compelling. Let's step back from the specific details about this object and think about something larger. Something about how we pursue knowledge, and what happens when we let certainty close our minds to possibility. History is filled with examples of things that seemed impossible until they weren't, ideas that were mocked until evidence made them undeniable, theories that destroyed careers until they became textbook foundations. If there's one lesson we should learn from history, it's that the boundaries of the possible are much wider than we think. For centuries, humans believed Earth sat motionless at the centre of the universe. Everything else, the sun, planets, stars, revolved around us. That made intuitive sense. The ground feels stationary, the sky appears to move, and it placed humanity at the cosmic centre, which aligned with religious and philosophical views about our importance. Astronomers who suggested otherwise faced serious consequences. Giordano Bruno was burned at the stake partly for proposing that Earth orbited the Sun and that countless other worlds existed. Galileo was forced to recant his support for heliocentrism. The idea seemed not just wrong but dangerous. It threatened established power structures built on the assumption of human centrality, until it didn't, until evidence became overwhelming, until the heliocentric model explained observations that the geocentric model couldn't account for, and then the impossible became obvious. Now we teach children that Earth orbits the Sun as basic fact. The idea that seemed radical enough to justify execution became elementary school science, or consider continental drift. For centuries, geologists assumed continents were fixed. Maps showed the same shapes in the same positions since ancient times. Yes, those shapes fit together suspiciously well. South America and Africa looked like puzzle pieces, but surely that was coincidence. When Alfred Wegener proposed that continents actually moved, drifting across Earth's surface over geological time, he was ridiculed. The idea seemed absurd. What force could move entire continents? Where was the mechanism? His peers dismissed him. His theory was called pseudoscience, until decades later, when evidence from seafloor spreading and plate tectonics confirmed he was right. Continents do move. The mechanism is convection in Earth's mantle. What seemed impossible was actually fundamental to understanding our planet's geology. Now we teach plate tectonics to children. Wegener was vindicated posthumously, but only after years of being treated as a crank. These stories repeat throughout scientific history. Continental drift, heliocentrism, germ theory of disease, evolution by natural selection, quantum mechanics. Each represented a revolutionary break from established thinking. Each faced enormous resistance. Each was eventually accepted because evidence demanded it. The pattern is always the same. Someone observes something that doesn't fit existing models. They propose an explanation that seems radical. The establishment resists because accepting the new idea requires abandoning comfortable frameworks. Eventually, evidence accumulates until resistance becomes untenable. The revolution happens, and the next generation wonders what took so long. We're living through one of those moments right now with the possibility of extraterrestrial intelligence. The question of whether we're alone in the universe is as fundamental as whether Earth moves or continents drift. The answer will reshape how we understand our place in reality. But there's enormous resistance to taking this question seriously. Not because evidence is lacking, not because the search is unscientific, but because the implications are uncomfortable. Because admitting we might not be alone challenges assumptions we've built entire worldviews around. Dr. Loeb's work sits exactly at this tension point. He's asking uncomfortable questions. He's proposing explanations that sound radical. He's facing resistance from institutions invested in conventional thinking. This is a familiar pattern. It's how paradigm shifts begin. That doesn't mean Loeb is right. Being ridiculed doesn't make you Galileo, sometimes it just means you're wrong. But it does mean his questions deserve serious investigation rather than dismissal. History teaches that revolutionary ideas always seem impossible at first. The key is testing them rigorously rather than rejecting them reflexively. What makes Loeb's approach scientific is that he's not asking anyone to believe him. He's asking them to look at evidence, to gather data, to test hypotheses. His claims are falsifiable. They make predictions. They can be proven wrong if observations don't match expectations. That's the difference between science and pseudoscience. Not whether claims sound strange, but whether they can be tested. Pseudoscience makes unfalsifiable claims, moves goalposts when evidence contradicts predictions, relies on anecdotes rather than data. Real science proposes testable hypotheses and follows evidence wherever it leads. Loeb is practicing real science. He's making specific claims about specific observations. He's suggesting measurements that would support or refute his hypothesis. He's open about uncertainty and willing to revise his assessment as new data arrives. That's exactly how science should work, but science is done by humans, and humans struggle with uncertainty. We want definitive answers. We want to know whether this object is natural or technological. We want certainty. But sometimes the honest answer is, we don't know yet. More investigation is needed. That's uncomfortable. It leaves us in limbo. It means tolerating ambiguity. But it's also the truth. And science is supposed to pursue truth even when it's uncomfortable. We need a culture that rewards intellectual courage, that celebrates scientists willing to ask questions their peers find uncomfortable, that funds investigation of anomalies even when they might have mundane explanations. Because the only way to find revolutionary answers is to ask revolutionary questions. This doesn't mean abandoning skepticism. Skepticism is crucial. It prevents us from accepting false claims. It keeps science rigorous. But there's a difference between healthy skepticism and closed-mindedness. Healthy skepticism says, show me the evidence and I'll evaluate it fairly. Closed-mindedness says, I've already decided this is impossible, so I won't look at evidence. When scientists refuse to investigate technological possibilities for interstellar visitors, that's closed-mindedness. When they dismiss anomalies without adequate explanation, that's dogma rather than science. When they attack colleagues for proposing unconventional hypotheses, that's tribalism. We can do better. We can hold our theories lightly and our evidence tightly. We can remain skeptical while staying open. We can demand rigorous proof without prejudging conclusions. And we can remember that the universe has surprised us before and will surprise us again. Reality is under no obligation to match our expectations. Nature doesn't care about our comfort. The cosmos reveals itself on its own terms. So when something unusual appears, an interstellar visitor behaving oddly, we should look carefully, gather data, consider multiple explanations, test them rigorously, and accept whatever conclusion the evidence supports, even if it's not what we expected. That's the attitude Loeb embodies. Whether he's right about this specific object or not, his willingness to ask uncomfortable questions is exactly what science needs. He's demonstrating that serious scientists can explore extraordinary possibilities without abandoning rigor. And he's reminding us that the greatest discoveries come from questioning what we think we know, from looking at familiar things with fresh eyes, from daring to imagine that the impossible might be real. Because sometimes the impossible is just the truth we haven't discovered yet. The object is out there right now. As you're hearing these words, it continues its journey through our solar system, silent against the cosmic background, indifferent to our debates about what it is, unmoved by our excitement or skepticism. It simply exists. It moves. It glows in ways we're still trying to understand. And it carries secrets we're only beginning to glimpse. Dr. Avi Loeb has given us a framework for thinking about this visitor. He's asked whether it might carry artificial intelligence, whether it might be a thinking machine from another civilization, whether we're being observed by technology we can barely comprehend. That question unsettles some people. The idea that we might be under observation, that privacy was always an illusion, that other intelligence has been watching our development, recording our history, analysing our nature. It excites others. The possibility that we're not alone, that consciousness exists elsewhere, that the galaxy is inhabited and we're part of something larger than ourselves. But regardless of how it makes you feel, it's a question worth asking. Because if we don't ask impossible questions, we'll never discover impossible things. If we only investigate comfortable possibilities, we'll only find comfortable answers. Science is not about certainty. It's about curiosity. It's about looking at the universe honestly and admitting when we don't understand something. It's about having the courage to propose explanations that sound absurd at first but might be true. Loeb embodies that spirit. So do the thousands of people who've written to him, thanking him for keeping wonder alive in an age that often feels too cynical for dreams. Those letters from students discovering their passion for astronomy, from grandparents who never stopped looking at the stars, from people in difficult circumstances who find hope in the vastness of space, remind us why this matters. We need a mystery. We need to know that something larger than ourselves might exist. We need possibilities that transcend our daily struggles and petty conflicts. We need reminders that we're part of a cosmos so vast and strange that we've barely begun to understand it. This object gives us that. Whether it's ice or intelligence, Whether it's natural or technological, it reminds us that the universe is full of surprises, that we don't have everything figured out, that wonder is still possible. In the coming weeks, we'll learn more, new observations will arrive, Dr. Loeb will update his assessment based on the best data we're likely to get. The mystery might deepen, it might resolve, but either way, we'll know more than we know right now. And even if this object turns out to be completely natural, just an unusual comet from another star system this moment, will have been worthwhile. Because we asked. Because we looked carefully. Because we took the possibility seriously instead of dismissing it reflexively. That's how discovery happens. That's how we expand the boundaries of knowledge. Not by accepting easy answers, but by investigating thoroughly when something doesn't quite fit. If you've stayed with me through this entire discussion, you're part of this journey. You're part of a community that asks big questions and isn't satisfied with superficial answers. You're someone who looks at the night sky and wonders what's really out there. That curiosity matters. That willingness to consider uncomfortable possibilities matters. That openness to mystery matters. Because the universe speaks to those who listen. It reveals itself to those who pay attention, and it saves its greatest revelations for those brave enough to ask questions others find too strange to consider. So, here's what I need from you. First, hit that subscribe button right now. We're going to follow this story as it develops. Every new observation, every update from Dr. Loeb, every development in our understanding of this object will cover it. You don't want to miss what happens next. This might be one of the most important scientific investigations of our lifetime. Second, share this video with people who care about these questions. The more minds thinking about this, the better our collective understanding becomes. The more people asking whether we're alone, the more pressure there is to investigate thoroughly. Your sharing matters. Third, drop a comment below. Tell me what you think. Do you find Loeb's hypothesis plausible, or do you think natural explanations will ultimately prevail? What would it mean to you personally if we discovered extraterrestrial artificial intelligence? How would it change your understanding of humanity's place in the cosmos? I read every comment, and your perspectives genuinely matter to this discussion. Fourth, stay curious. Don't let anyone shame you for asking big questions. Don't let certainty masquerading as sophistication close your mind to possibilities that sound impossible at first. The universe is stranger than we imagine. It's stranger than we can imagine. And somewhere out there, answers are waiting for us to find them. This object might be the key that unlocks those answers, or it might be natural and some future visitor will provide the evidence we're looking for. But either way, we're living through an extraordinary moment, a time when we have the technology to detect interstellar visitors, the scientific frameworks to analyze them rigorously, and the courage, at least some of us have the courage to ask whether they might be more than rocks and ice. We're developing capabilities previous generations only dreamed about. We're asking questions that were once pure philosophy and turning them into testable science. We're standing at a threshold, and what we discover on the other side might transform everything about how we understand ourselves and our universe. So stay with me, keep watching, keep questioning, keep wondering, because this object is just the beginning. There will be others. Our detection capabilities will improve. Our analytical methods will refine. And someday, maybe with this visitor, maybe with the next one, maybe decades from now, we'll find the evidence that settles the question of whether we're alone. And when that moment comes, I want you to remember that you were here. You were paying attention. You were part of the community that took these questions seriously when others dismissed them. You were someone who looked up at the stars and had the courage to imagine that something might be looking back. Let's find out together what comes next. Let's see what the universe has to teach us. Let's stay open to possibilities that sound impossible and see where the evidence leads. Because out there, millions of miles away, an object continues its journey. And whether it's thinking about us or not, we're certainly thinking about it. We're wondering. We're investigating. We're doing what humans do best, looking at something mysterious and refusing to look away until we understand. That curiosity is our greatest strength. That wonder is what makes us human. And that refusal to accept comfortable lies over uncomfortable truths is what will eventually answer the oldest question our species has ever asked. Are we alone? Stay curious, stay engaged, and let's find out together.